Hey everyone, this is Muhammad.nadeem and welcome to my YouTube channel. Today's lecture about the force between two parallel current carrying conductors. So here we have the two conductors which are labeled by the red colors, and these two conductors are connected through these wires with this battery. This side of the battery is the positive and here is the negative terminal of the battery, and the conventional current in this circuit will flow in this direction. So here is the direction of the conventional current from the positive terminal of the battery, and that current will pass through this conductor in this direction. And when it passes through this conductor here, will through this wire, it will pass through this conductor in this direction, and in this way it will complete the whole circuit. Now, if the current is passing through this conductor in this direction, so I'm going to pause this. So here the direction of the current from this conductor is this. Now, according to the right hand rule, the thumb, we will put the thumb in the direction of the conventional current, and the curly fingers will represent the direction of magnetic field. Here the current is passing in this conductor in this direction. So according to this right hand rule, our thumb will be in this direction, and the magnetic field will be produced around this in this direction. So here is the direction of that magnetic field produced around this conductor. So if I consider the compass here in this position, and the magnetic field of this current, the magnetic field of this conductor will pass through this compass in this direction. So here is the direction of the um, magnetic field from this conductor, and here we have the compass. So therefore this side of the compass will be the this side of the compass will be the north. Okay, this side of the compass will be the north and this side will be the south. And similarly, when the current is passing through this conductor in this direction, according to the right hand rule, our thumb will be in this direction. Okay. And according to this rule, the magnetic field will be produced around this conductor in this direction. Okay. Here is the curly finger will be in this direction. And if we consider the compass here is a test magnet, and as the direction of magnetic field around this conductor is in this way. So here is the direction of that magnetic field which are produced by this conductor, and here according to this the needles of the compass will be arranged in this way. So here this side will be the south, and this side of the test magnet will be the north. So there will be the force of repulsion between these two uh, poles of the magnets, and similarly there will be the force of repulsion between these two poles of the magnets, and therefore these two conductors repel each other. Now, if we connect these two conductors in parallel circuit, so here we have the parallel circuit, and these are the two wires connected parallel to each other, and then these two conductors through this wires are connected to this battery. So this side of the battery is the positive, and here is the negative terminal of the battery. And in this circuit, the direction of the conventional current is this, and it will pass through this wire in this direction, and here it will reach here, and the direction of the conventional current here will be this, and in this junction the current will distribute it here in this side and also in this side. So here in this case, the direction of the conventional current from this conductor is this, and similarly, the direction of the conventional current from this conductor is this. So now when the current is passing through this conductor, the magnetic field will produce around this conductor. Now, according to this right hand rule, the we will put the thumb of our right hand in the direction of the conventional current. So if we put that thumb in the direction of the conventional current, the magnetic field will produce around it, and here the magnetic field will produce around this conductor. And now I'm going to label that. So this will be the direction of the magnetic field around this conductor. And similarly, when we put our fingers in the direction of the conventional current, so here the magnetic field will produce from this conductor, and the direction of that magnetic field will be this. Okay. So, if similarly, if we consider uh, if we consider the test magnet here as a compass, the magnetic field of the conductor will pass through this compass in this direction. So here is the direction. So that will pass through this in this direction. Okay. So due to which this side of the compass will this side of the compass will be the south, and this side of the compass will now be the north. And similarly, when the current is passing through this conductor, the magnetic field will produce around this. And here, if we consider the compass, then the magnetic field will pass through the magnetic field of the conductor will pass through this compass, and will pass through this compass in this direction. So here this is the direction of the magnetic field of this conductor. So due to which this side of the due to which this side of the compass will be the north, and this side of the compass will be the south. So um, here this is the south and this is the north. And similarly, this is the north and this is the south. So in this south will attract this north. So here this is the force of attraction between them, between this south and this north. And similarly, there is the force of attraction between this north and the south. Therefore, these two wires, when connected in parallel circuit, they will attract each other. So this is the physics behind that. So I'm going to pause this, and here in this way, these two wires are attracting each other. The magnitude of the attraction. So here, the magnitude of the attraction will be more for this internal circle, and this is will be increased if the radius of it will the magnitude of the attraction between these two currents will be increased if we decrease the radius of this circle. So if the radius of the circle is increased, then in that position, the attraction between these two wires will be less. So here, um, in this position, the attraction between these two wires will be less. This is because here the radius of this circle which connect each other, so that radius of this circle is more. If the radius of the circle is more, then the attraction will be less. So when the radius is less, so here the radius of this circle and the radius of this circle which coincide each other are less, therefore the force of attraction here will be more. So, in simple words, we can say that if these two conductors are bring near to each other, the force, the magnetic force, mean the magnetic induction will be more. And if we bring these two wires away from each other, that force will be less. Okay, as we discussed in the previous lecture, that b b is the magnetic induction. So here we have the b is inversely proportional to the radius of the Empyrean loops. So we will discuss this in more detail in the next video as well. But this was the physics and logic behind the attraction and repulsion of the two parallel current carrying conductors. So that's it, guys. Thanks for watching.